So we are going to discuss with starting with the 151, right? 151 to 165, right? Those are the MCQs we are going to discuss today, right? So let's start with the 151, right? But question number 151. Right. See what it says. First statement. See, it says HI turns a solution of acidified dichromate to green. HI turns a solution of acidified dichromate, potassium dichromate, to green. Let's see what happens. So, if the HI is to react, right? Here you have the -1 oxygen state of iodine with the acidified dichromate in acidic medium, right? This is in acidic medium, right? Here also the acidic medium provides, and they are saying acidified dichromate, right? Cr2O2 minus potassium dichromate provides this ion, right? So what will happen? The HI will oxidize to I2 aqueous to the zero oxygen state, while dichromate, right, will reduce to plus Cr3 plus aqueous, right? So what are the colors of these things? So basically I2 aqueous solutions. I2 aqueous solutions are brown colored. Brown colored. So in acidic medium, Cr3 plus are in acidic medium is acidic. Acidic Cr3 plus is actually greenish, green colored. So final solution would be kind of greenish brown, right? That would be the final solution, right? Not just the green, because I2 is also produced, so that the final solution would look like greenish brown or brownish green, right? Greenish brown solution would be the result. So again, let's go to the statement. It says HI turns a solution of acidified dichromate to green. So it is false. The color is not green. The color is brownish green, because the I2 is also produced in this case, right? So the first statement can be taken as false. Let's see the second statement. Second statement says aqueous Cr3 plus ion solution is green in color. No, it is false. The acidified Cr3 plus ions are the green colored stuff, right? The aqueous Cr3 plus, the aqueous Cr3 plus means CrH2O6 3 plus thing, that is purple in color, right? So aqueous Cr3 plus means CrH2O6 3 plus. Actually, that guy is purple in color. What is green is actually the acidic medium Cr3 plus. Acidic Cr3 plus. That means this ion, if you have to acidify the medium with use of HCl, it would be this. Or if you have to acidify the medium with use of H2SO4, the complex would look like this. Anyway, these solutions are greenish. So greenish solutions are the acidic Cr3 plus solutions, not the aqueous Cr3 plus solutions. Aqueous Cr3 plus solutions are purple in color. So we have to take the statement as a false statement there. So because they are indicating the aqueous thing is green in color. So both the statements are false. So the answer is going to be answer number 5. Answer number 5. Okay. So just go to the stuff. Right now, let's move to the question number 152. Right. So 152. See, first the first statement. See what it says. Cu2 plus and Al3 plus could be identified separately using an aqueous solution of ammonia. An aqueous solution of ammonia. See what we could think of. So ammonia, aqueous ammonia, right, will provide OH minus science solution. As it is weakly basic, right, can provide OH minus science solution, right. So what will happen if you add the ammonia to Al3 plus as well as copper 2 plus? With the copper 2 plus science, the aqueous ammonia will produce first the copper hydroxide, PPT, which is a blue colored. So as copper is coming up as a D7 to D10, as a D7 to D10 cation, right? The excess ammonia addition will dissolve this one to form the amine complex. This is how the copper acts with ammonia. This solution, which is dark blue colored. This is how the copper 2 plus reacts with ammonia. So when it comes to aluminium 3 plus, that is our next cation, right, with ammonia, as ammonia is able to provide the OH minus solution. So first it will produce the aluminium hydroxide, which is a white PPT. Further, no more reaction could occur as aluminium is not coming as a D7 D10 cation, right? So this is how the things will looks like when they are to react with ammonia, right? Even you are to add excess ammonia, still the white PPT will be the result with the A3 plus science, right? So we clearly see we can use the NH3 as a reagent to differentiate the copper 2 plus as well as the Al3 plus science, right? So basically, you will come up with different colored hydroxide precipitates as well as the copper hydroxide precipitate will dissolve when you add excess ammonia. So with those characteristics with the copper, basically we can identify the copper, right, distinguish the copper and the Al3 plus, right. So the first statement can be taken as true, as they are saying copper 2 plus and Al3 plus could be identified separately using an aqueous solution formula. Yes, we can. So this is true. The second statement. See what it says. Aluminium hydroxide has amphoric properties. Yes, that is true. Right? All the hydroxides of amphoric metals are amphoric. All the hydroxides of amphoric metals are amphoric. So as aluminium is kind of an amphoric metal, so aluminium hydroxide is also amphoric. Right? As Al is an amphoric metal, its hydroxide, the AlOH3, is also amphoric. Yes, the statement is true. The statement is true. So aluminium hydroxide is amphoric. But for the differentiation of these two things is not because of the amphoric nature, but because of the D7 to D10 nature of the copper 2 plus, right? So ammonia is a reagent, right, which will be used to identify the D7 to D10 cations. Ammonia is a reagent which can be used to identify the D7 to D10 cations, not the amphorics. To differentiate the amphoric from the other metals, we have to use a strong base. We have to use a strong base to come up with the hydroxide complexes there, right? So the second statement won't explain the first one, so that we have to come up with the answer number 1, right? So answer number 2, sorry, right? So I'll come up with some more comment here, right? That's why we are choosing the number 2, right? NH3 is used to differentiate or identify, let's say identify D7 to D10 cations as they form amine complexes with NH3, right? So next one, the strong bases. Some example, NaOH, maybe KOH, barium hydroxide, are used to identify amphoric cations as they form hydroxide complexes, as they form soluble hydroxide complexes, right? So the amphoric nature can't be identified with the use of NH3. The amphoric nature can be identified with the use of a strong base, not a weak base like NH3. This guy is a weakly basic, that is not being able to identify the amphoric nature. To identify the amphoric nature, you need a strong base. I think you got the idea, right? So second statement won't explain the first one, right? The differentiation is done with the use of NH3, that is used to identify the basically differentiate the D7 D10 out of the two, right? To distinguish the amphoric cation, we may have to use a strong base. but they have used the NH3, which is a weak base. Right? No? Got the idea? So the answer should be the answer number 2. Right? Just have a note. So here now my excess addition of ammonia do nothing here, right? If you need excess ammonia addition, do nothing to these guys. Do not dissolve. Just the ALOH stands, right? Right, no? So let's move to the question number 153. So 153. See what it says. The first statement, first of all. Yes, it says a sample of BaOH2 cannot be used to identify NH4Cl and NH4SO4. Right, let's see. So they are adding barium hydroxide to ammonium chloride as well as to the ammonium sulfate. Right? This is barium hydroxide is added. Barium hydroxide is also considered as a strong base, right? Strong base. Any metal hydroxide which is not going to precipitate can be referred to as a strong base, right? So in S block, only the beryllium and magnesium get precipitated as hydroxides. So the barium hydroxide is not a precipitate. So any metal hydroxide which is not a precipitate can be considered as a strong base, right? So this is a strong base, right? So what would be the reactions available here? So ammonium salts can be taken as a combination of ammonia and the corresponding acid. Here it is the ammonia, 2 of ammonia plus the H2SO4, the corresponding acid of the anion there, right? See, so what will happen? Here the ammonia will release, first the ammonia will release, then this acid will react with this base, HClBaOH2. So the salt and H2O will be the result. The salt is BaCl2 and H2O, salt and H2O, right? HCl and BaOH, right? Just sign exchange, right? H plus goes with the OH minus, the H2O, Ba2 plus goes with the Cl minus, the BaCl2, right? The things are clear. So to balance this one, so you need 2 of HCl to form the 2 of H2O. So this becomes 2, right? Yeah, so right. Then when it comes to this one, it is going to be the 2 of NH3 will release first of all, and then this acid will react with the base, the H2SO4 and BaOH2. That will give you the salt, Ba sulfate, barium sulfate, and the 2 of H2O. Here the barium sulfate is considered as a white PPT. White PPT. Here this is a just a colorless solution. no halide in S block get precipitated, right? All the halides in S block are solutions. So this is a colorless solution, while this is a white PPT. Yes, so that we can use barium hydroxide to differentiate the ammonium chloride and ammonium sulfate. With the ammonium sulfate situation, you get a white PPT as Ba2 plus ions are capable of precipitating the sulfate anions, right? So the statement 1 can be taken as true. Yes, barium hydroxide can be used to differentiate the two ammonium salts here. Let's copy the second statement. See what it says. Both compounds NH4Cl and NH4 sulfate form ammonia with barium hydroxide. Yes, ammonium salts when reacting with strong bases, ammonia will be produced, right? All ammonium salts produce NH3 gas when reacting with strong bases, right? Barium hydroxide is strong base. So it comes strong bases. The knowledge you should know is, right, any metal hydroxide which won't precipitate can be referred to as a strong base. So barium hydroxide is a strong base. So example, barium hydroxide is soluble, that means strong base, right? So ammonium salts with strong bases produce ammonia. Yes, the statement is true. Both the statements are true, but the second one won't explain the first one, right? The differentiation could be done because of this precipitation, right? That is, no mention about that thing. So both are true, but second won't explain the first one. So better to go with the answer number 2. That is the review for the 153. No? The first statement is false, no? So they are saying cannot be used. They are saying cannot be used. So if they are saying cannot be used, it is false. First statement they are saying cannot be used. No, we can use, right? So division can be done as a precipitated form here. So answer should be answer number 4. False and true means it's number 4, right? One 54. See, first the first statement. See what it says. Addition of ammonium chloride followed by ammonium hydroxide into an aqueous solution containing magnesium 2 plus do not form precipitates. So addition of ammonium chloride with ammonium hydroxide. So that reagent is used in group 1 group 3, right? It's kind of a reagent used in group 1 group 3, right? So ammonium chloride with ammonium, these two ways, right? Ammonium hydroxide. Reagent used in group analysis. Group 2. Right now? Okay. With this one, actually we are providing very low amount of OH minus concentration. With this one, we are providing very low amount of OH minus concentration that won't be enough to precipitate the high KSP high KSP hydroxides. High KSP hydroxides. With this one, right, only the low KSP hydroxides can be precipitated. Only we have three of those, right? The 3 plus hydroxides, Fe3 plus, Al3 plus, chromium 3 plus. Those 3 plus hydroxides can get precipitated as those are with kind of a low KSP value, right? With very low amount of OH minus provided by this reagent, right? We can precipitate only those, not the high KSP sulfides. Not the high KSP hydroxides like the magnesium hydroxide and the 2 plus hydroxides, right? That is the theory there. So basically, magnesium hydroxide can't be precipitated with the use of this reagent. If you are just adding only the ammonium hydroxide, yes, it can precipitate the magnesium hydroxide, even the 2 plus hydroxides, but not the ammonium hydroxide with the ammonium chloride, right? So the theory here is actually like this, right? So you have the NH4OH ions, which provides the OH minus ions to the medium. But what happens here is, as with the NH4Cl, right, with the NH4Cl, as NH4 plus amount is high here, right? What happens? To reduce or decrease the amount of this thing, the reverse reaction favors for this equilibrium, so that when the reverse reaction happens, the OH minus consumes, OH minus reacts and consumes. So low amount of OH minus will be provided to the medium with this reagent, right? Very low OH minus concentration will be provided by this reagent. So, only the hydroxide precipitates, only the hydroxides which are with low KSP values. What are those? Basically these guys. AlOH3, the 3 plus hydroxides. CrOH3, FeOH3. Can get precipitated by this low OH minus concentration. Right? So so the 2 plus hydroxides can't get precipitated, right? So magnesium hydroxide do not precipitate there. So magnesium hydroxide won't precipitate, as it's a high KSP hydroxide. 2 plus hydroxides are high KSP hydroxide. You may need some greater OH minus concentration, right, to get precipitated there, right? The 2 plus hydroxides. So those are high KSP hydroxides, right? So that is the theory behind this situation. So let's go to the statement again. Addition of ammonium chloride followed by this thing to aqueous solution containing magnesium do not form precipitates. Yes, that is true. That is true. Right, no? Statement is true. Right? Okay. Second statement, both compounds MgOH2 is soluble in NH4OH, right? Next one, the second statement is what it says: magnesium hydroxide is soluble in NH4OH. No, it is false, right? To dissolve in NH4OH, your metal hydroxide should be coming from a D7-D10 cation, right? To dissolve in excess of ammonia, your metal hydroxide should come up with a D7-D10 cation. Magnesium hydroxide is not such a thing, right? Magnesium 2 plus is not a D7-D10 cation, so there's nothing to do with the right solubility with ammonia for this case, right? So, right, metal hydroxides, right? The metal hydroxides with D0D10 cations will dissolve in aqueous ammonia. This is also known as the ammonium hydroxide. Aqueous ammonia is ammonium hydroxide, right? So, magnesium hydroxide is not a such, right? Right. So, magnesium hydroxide is soluble in ammonia means it's false. It's false. Right. So, true and false means answer should be answer number 3, no? 154, it should be the answer number 3. Right. See, this is just a bit about the theory behind this KSP stuff, how those things relates to these OH mass concentrations and the things, right? Right, it's like this. Let's think of the group and this group 3. Right? So let's concern two situations where you have a 3 plus cation and a 2 plus cation. Let's say you have a 2 plus cation here. You have 3 plus cation here. See, this one is 2 plus. This one is 3 plus. Right? To precipitate the hydroxides, as this guy's charge density is low, so charge is low, that means charge density is low, right? So to attract the anions there, basically anions should come very closer towards these anions, to the cations, right? Anions should come much closer to the cations, right, to attract those hydroxide anions to get precipitated, right? So that means you should have some greater OH minus concentration to get precipitated here with a 2 plus charge situation. But with the 3 plus charge situation, as its charge density is very high, it can attract even the anions far away from the cation. Still the attraction can be done. as their charge density is very high, or one can say the charge is very high. They can attract even the anions which are very away from the cation. But here the anions should be very close to the cation. If not, the attraction can't be done. So that here to get precipitated, very high OH minus is needed. High OH minus concentration. In deuterium, you have more ions, right? Concentration needed to get precipitate. When it comes to plus 3, guys, right? Low OH minus concentration would be sufficient to get precipitated. Right? So KSP is what? KSP is actually a measure of these ions at the moment of precipitation. KSB is the measure of, it's kind of a measure of ions at the moment of precipitation. Right? KSP is a measure of ions at the moment of precipitation. Right? Okay. So normally for MOX in, the charge is in, right? So KSP can be written as like M in plus OH minus, as you have n times of OH minus, it is OH minus squared. This is how, sorry, OH minus n times. This is how it is written, right? So it is like you have one Mn plus ion and n times of OH minus ion. This is like this. If you are thinking of FeOH2, so FeOH2, actually this contains one Fe2 plus ion and two of OH minus ions, no? Like this, no? Or FeOH2. That means KSP is, the KSP is Fe2 plus OH minus OH minus. This is what we refer to as OH minus squared, OH minus squared ultimate. So that's how we write, right? FeOH2, that means Fe2 plus OH minus, this 2 is squared, the power, right? That's how the KSP comes, right? Okay, so see, in this case, if you have to apply the KSP stuff here, right, we can write it as KSP is equal to, right, M2 plus M2 plus thing, no? And OH minus, right, squared, right? So in this case, KSP is equal to M3 plus and the OH minus cube here. So anyway, this value is very small, but here the value is large. Right? So the KSP value would be large here. More ions are there. KSP value will be small here. Right? It's just a measure of ions. So if you have less ions, the KSP is less. If you have greater number of ions, the KSP is high. That is what you should know, right? Don't worry about these powers here. Don't worry that much about these powers. Right? Yes, if you are taking a physical meaning, it is all about the ions at the moment of precipitation. If you have more ions at the moment of precipitation, the KSP is high. If you have less ions at the moment of precipitation, KSP is low. Is what it means, right? So when it comes to that reagent used in the group 3, right, that provides very low amount of OH minus ions. That provides very low amount of OH minus ions. So that means only the low KSP, with the low amount of OH minus ions, only the low KSP hydroxides can get precipitated, but not the high KSP hydroxides, right? With the low amount of OH minus, you can't get precipitated these high KSP hydroxides because it needs some high amount of OH minus concentration to get precipitated like this. That is the idea. That is how the KSP thing will be related to the concentration of OH minus at the group and group 3, right? So these same concept can be applied even for the group 2 and group 4 analysis with the sulfide ions. When it comes to metal sulfides, the same logic can be applied, right? Okay, yes, actually something to do with the charge density as well, the charge of ions, right? Never forms a stable state with excess ammonium hydroxide. Let's see what happens there. So you have magnesium chloride and nickel chloride, no? So magnesium chloride and nickel chloride. Here the nickel 2 plus is considered as a D7 to D10 cation, right? So if you add some ammonium hydroxide, right? If you add some ammonium hydroxide, right? So it's like you add in some excess ammonia. So let's go through step by step, right? If you add some ammonium hydroxide first of all, right, it will produce the magnesium hydroxide, white PPT. The excess ammonia addition do nothing, right? Won't dissolve the precipitate because it is not a D7 D10 hydroxide. Right? If you add excess ammonium hydroxide, that does nothing, right? Do not dissolve. That means magnesium hydroxide precipitate stands. Right? So what with the nickel chloride situation? So nickel is considered as a D7 D10 cation. So nickel 2 plus, right? So first it forms the hydroxide, as ammonium hydroxide is kind of weak base, the hydroxide precipitate, right, which is green in color. And excess addition of ammonium hydroxide, that means excess ammonia is added, it will form the amine complex as it's a D7 D10 cation, right? The nickel 2 plus. This is how it looks like now. This is a solution. This is a solution which is blue in color. Right? This is how the things would look like. Let's go to the statement again. Magnesium chloride forms a white PPT with excess ammonium hydroxide, while nickel chloride never forms a stable precipitate with excess ammonia. Yes, with the excess ammonia, it's not a stable precipitate. It's the amine complex. It's the amine complex. Right? With the excess ammonia, you form the amine complex. Solution. No precipitate is formed with the excess ammonia. With the excess ammonia, it goes towards the amine complex. So no stable hydroxide precipitate can be formed with the excess ammonia by a D7 D10 cation, right? So the statement is true, right? As this one is not a D7 D10, the hydroxide won't dissolve in excess ammonia. But as this one is a D10, D7 D10 hydroxide, it will dissolve in excess ammonia. So the hydroxide precipitate is not stable in excess ammonia medium, right? For the nickel hydroxide, for a D7 D10 hydroxide, right? So the statement can be taken as true. Right? Let's move to the second statement. Nickel 2 plus ions form a soluble amine complex with excess ammonium hydroxide, but magnesium 2 plus do not form a soluble complex. Yes, That is the idea. Ne? Point is only, right, D7 to D10 cations are able to form amine complex, form soluble amine complex mixes with excess ammonia, or one can say conc ammonia. Right? No? So the second statement is also true. So that will explain the first statement. No, that will explain the first statement, right? Because of this, the nickel is not able to form the hydroxide precipitate when you add the excess ammonia, right? It will form the amine complex instead, right? So both statements are true, and second one explains the first one. So we can take the answer as answer number one. Right? No? Right. Let's move to the question number 156. Right. See first the first statement. See what it says. Nickel 2 plus solution do not produce a black precipitate of nickel sulfide with H2S in DIL HCl medium. Right, nickel 2 plus, yes, it get precipitated with the group princess group 4, right? This is all about the reagent of the group princess group 2, right? H2S in DIL acidic medium, right? H2S in DIL HCl medium is the reagent of group princess group 2, right? They are nickel 2 plus won't get precipitated, right? Okay, see the theory behind that thing, right? With the group princess group 2, right? So H2S is added, right, in an acidic medium. In an acidic medium. So what will happen? So the medium is acidic. That means high H plus concentration is there in the medium. So that to reduce the H plus amount, the reverse reaction will be favored. So that right, when the reverse reaction favors, right, the sulfide ions will react to do the reverse reaction, so that sulfide ion concentration drops. Right. So with this reagent, very low amount of sulfide ions will be provided. Very low concentration of H2 minus ions provided. So with a very low concentration of H2 minus ions, only the metal sulfides which are with low Ksp values. With very low concentration, the metal sulfide which are with very low Ksp values can get precipitated, right? So only metal sulfides with low Ksp values. Low Ksp values are able to precipitate. What are sulfides with low Ksp values? Those 9 sulfides, right? We see with the group and group 2, right? Low Ksp values. What are those? From the D block, it is the copper sulfide, mercury sulfide, and the cadmium sulfide. Right? From the B block, you have from the group 14, tin 2 sulfide, tin 4 sulfide, lead sulfide. On the group 15, arsenic sulfide, antimony sulfide, bismuth sulfide. Only these guys get precipitated. But not the nickel sulfide. Not the nickel sulfide. Right? Nickel sulfide, cobalt sulfide, manganese sulfide, and zinc sulfide are with high Ksp values. Which need high concentration for H2 minus to get precipitated. For high H2 minus concentration to get precipitated. So they won't precipitate here. Got the idea, right? So again, let's go to the first statement. Nickel 2 plus solution do not produce a black precipitate of nickel sulfide with H2S in acidic medium. So that is true. The statement is true. The reasons are very clear. See the second statement. Nickel sulfide is readily soluble in HCl. That is true. Huh? So second statement. Metal sulfides will dissolve in HCl, right? So basically, if you are adding some sufficient amount of dill acids, right, the sulfides will dissolve. Remember, Lamai, in this case, with this situation, normally they are adding some HCl with some considerable concentration. No? They are adding some HCl with considerable concentration, right? So some sufficient amount of H plus is provided. All the sulfides can be dissolved, right? Even the group 2 sulfides. In dill acidic medium, you see that group 2 sulfides are not dissolving. That is why they get precipitated, right? But if you are to supply some sufficient amount of sulfide, some sufficient amount of H pluses, they definitely get dissolved, right? You can lamai then because සාමාන්‍යයෙන් අර HCl මෙතන අපි use කරනවා කියලා දන්නවා සාමාන්‍යයෙන් හිතන්නකෝ මේ 2 මෝල වගේ use කරනවා කියලා 2 මෝල වගේ use කරනවා group analysis වල හරිද හිතන්නවා 6 මෝල වගේ දැම්මා කියලා 6 මෝල HCl solution එකක් දැම්මොත් මේ ටිකක් dissolve වෙලා H2S gas එක release වෙනවා හරි group analysis වල right use කරන dill HCl කියන එක සාමාන්‍ය 2 මෝල වගේ ඒ වගේ amount එක තියෙන්නේ හැබැයි 6 මෝල කිව්වත් ඒකත් ඩීල් තමයි. අපි මේ ඩීල් ගැන කතා කරා කලිනුත් නේද? ඒ කියන්නේ ඔයාලමයි ඔයාගේ අර concentrated bottle එකෙන් දැම්මොත් තමයි concentrated HCl කියන්නේ. ඒකට වතුර පොඩ්ඩක් හරි දැම්මම ඒක ඩීල්. හරි වතුර පොඩ්ඩක් හරි දැම්මම ඒක ඩීල්. මේ 6 මෝල කියන්නේ ඩීල්. 2 මෝල කියන්නේ ඩිල් 0.1 මෝල කියන්නේ ඩිල් තමයි. ඔයාගේ අර දුන් දාන කන්සන්ට්‍රේටඩ් බොටල් එකකින්ම දැම්මොත් තමයි අපිට කන්සන්ට්‍රේටඩ් ඇසිඩ් එකක් කියලා කියන්නේ. මේක මීට කලින් කතා කරලා දිනවා කොන්කෙච්චනොට්‍රී කියලා කියන්නේ අර කෙන 16 mHනොට්‍රීට කෙලින්ම අර දුන් දාන බෝතලින්ම දාන්න ඕනේ. ඊට වතුර පොඩ්ඩක් කර දැම්මම it's considered as a deal situation. හරි. ඒ ඩිල් සිටුේෂන් එකෙත් අපි යූස් කරන කන්සන්ට්‍රේෂන්ස් අනුව වැඩි කොට දාගන්න පුළුවන්. දැන් මේක සාමාන්‍යයෙන් 2 mol HCl එකක් වගේ සාමාන්‍යයෙන් කරනවා. එතකොට ප්‍රෙසිපිටේට් උනාට 6 mol හරි 7 mol 8 mol වගේ කන්සන්ට්‍රේෂන් දැම්මොත් මේවත් ඩිසෝල්ව් වෙනවා. කොන්ක් HCl දැම්මොත් අනිවාර්යෙන් මේවා ඩිසෝල්ව් වෙනවා to produce the HCl to produce the H2S gas. මොකද සල්ෆයිඩ් කියන කට්ටිය නැන්නේ ඉන්නවා නම් අපි දන්නවනේ ඩිල් ඇසිඩ්ස් එක H2S gas එක ප්‍රොවයිඩ් වෙනවා කියලා. හරි ඩිල් ඇසිඩ්ස් එක H2S gas එක රිලීස් වෙනවා කියලා. හරි. તો ගෲප් පැනින්සල් යූස් කරන කන්සන්ට්‍රේෂන් එකක් එක්ක ගැටලුවක් නැහැ. එයාලා ප්‍රෙසිපිටේට් වෙනවා. හැබැයි ගෲප් පැනින්සල් යූස් කරන කන්සන්ට්‍රේෂන් වඩා වැඩි කන්සන්ට්‍රේෂන් එකක් HCl දැම්මොත් අනිවාර්යෙන් මේගොල්ලෝ ඩිසෝල්ව් වෙනවා. හරි. ඒ අයිඩියා එක ඔළුවේ තියාගන්න. හරිද? ගෲප් පැනින්සල් යූස් කරන ඩිල් HCl එක මෙයා ඩිසෝල්ව් වෙන්නේ නැති වුණාට හිතන්නකෝ මෙයා 2 මෝල කියලා. හැබැයි 6 මෝල එකක් දැම්මොත් මේගොල්ලෝ ඩිසෝල්ව්ලා H2S gas එක රිලීස් කරනවා. හරිද? දැන් ඔයගොල්ලෝ දකින්න ඇති මේ ප්‍රෙසිපිටේට්ස් ගත්තට පස්සේ උනත් දැන් ගෲප් පැනින්සල් අපි කතා කරද්දී ඔය ටේබල් එකේ ක්වෙස්චන්ස් කතා කරද්දී alright after obtaining the precipitates we use the dill nitric to dissolve this stuff and get the cation to the solution for the further analysis. ඔයගොල්ලෝ අර ටේබල් එක ගත්තට පස්සේ උනත් මේ ටේබල් එකේ කතා cations ලා ඔය question type වල නේද? අර ටේබල් type question ආවට පස්සේ හරි මුලින්ම precipitate එක obtain කරාට පස්සේ you just use the dill nitric to dissolve this stuff to get the cations to the solution for the further analysis. तो dill acid වල මේගොල්ලෝ dissolve වෙනවා. dissolve වෙන්නේ නැහැ කියලා දෙයක් නැහැ. අර මේ මෙතන group pencil use කරන HCl concentration එකත් එක්ක මෙයාලා dissolve වෙන්නේ නැහැ තියෙනවා. හැබැයි group pencil use කරන dill HCl වලට වඩා වැඩි concentration එක dill HCl දැම්මොත් වාගේ මෙයාලා ටිකක් dissolve ලා H2S gas එක release වෙනවා. හරි. ඒ idea එක තියාගන්න. ඒක වැදගත් කාරණයක් right? කොහොමුණත් ඉතින් ඒ වගේ ඉතින් ඕනම metal sulfide එකක් ඔයා sufficient amount of concentration if the sufficient amount of concentration is provided by the dill acid will dissolve to produce the H2S gas, right? Any metal sulfide, even the group 2 sulfides, right, will dissolve in dill acids to produce the H2S gas if you are coming up with sufficient amount of the dill acid, sufficient concentration of dill acid, right? Remember that, right? So if sufficient concentration of dill acid is used, any metal sulfide any metal sulfide කියලා ගොල්ලෝ මෙහෙම කරන්නේ නැති එකම එක සල්ෆයිඩ් එකක් තියෙනවා. ඒක අපි සිලබස් එකට දාලා දෙන්නේ නෙමෙයි පොඩ්ඩක් දැනගෙන ඉන්න. mercury sulfide එක. mercury sulfide වෙන ගේස් එකක්. මේක හොයා ගන්න බෑ මොකද්ද රීසන් එක කියලා. ඌ අර abnormal behavior තියෙන mercury sulfide කියන එක විතරක් dissolve වෙන්නේ නැහැ. ඒක වෙනම ගේස් එකක්. වෙනම ස්ටඩි කරලා බොහොම දෙයක් right. ඒක මේ පොයින්ට් සිලබස් එකේ නැහැ. හැබැයි අපි කීගෙන ගත්තේ හරියට මේකමකෝ. mercury sulfide කියන එක විතරක් dissolve වෙන්නේ නැහැ. ඒක ස්පෙෂල් ගේස් එකක් නේ. ඔය black color sulfide ලගේ black color sulfide තුනක් ඉන්නවනේ මෙතන. black color sulfide ලගේ right mercury එනවනේ. copper mercury මේ හතර black color sulfide හතරක් එනවනේ. මේ black color sulfide හතරක් වුණාට මම කියන්නේ මේ ඔක්කොම sulfide 9 වුණත් dill nitric වල dissolve නැති එකම එක sulfide එකක් තියෙනවා මෙන්න මු. හරි mercury sulfide. ඒක ස්පෙෂල් ගේස් එකක්. ඒක සිලබස් එකේ කතා කරන්නේ නැහැ. නමුත් අර කොලම්බස් කුස් පේපර්ස් වලින් අහනවා. මට ඉතින් අර ආතල් එකට ප්‍රශ්න අහනවනේ හරි. දුකට ඔය ප්‍රශ්න අහලා තියෙනවා. ඒ මම කියන්නේ මම ඉනි කියද්දි මම මේක ලියන්න නැත්නම් හරන්නේ නේ මොකක් හරි පොයින්ට් එක කරන්නේ ඒක. හරි. සාමාන්‍ය කතාව හරි මම මේක මෙතන mercury එක දාන්න. අර ඔයගොල්ලෝ knowledge එක නිසා මේ හැබැයි සිලබස් එකේ නැති දෙයක්. නමුත් ඉතින් දැනගන්න එක හරි දැනගන්නේ මෙච්චර කරන දේ නේ මෙච්චර මේක කතා කරන එක නේද? ඔක ඔලුවට දාගත්ත රවුලක් නැහැ. right? ඒතොර එහෙනම් right other than mercury sulfide, if sufficient concentration of dill acid is used, any metal sulfide will give H2S gas. or H2S gas එක release කරනවා and get dissolved. හරි කතා පැහැදිලි එහෙනම් right වාගේ statement එක හරි nickel sulfide කියලා නැහැ nickel sulfide වෙනවත් right with HCl nickel chloride and H2S will be produced right now so the statement right what it says the statement it says nickel sulfide is readily soluble in HCl it is true so both are true but that thing won't explain this one right this is some other case right providing some low amount of sulfides and stuff right this is some normal stuff right both are true but the second statement won't explain the first one right so answer can be taken as 2 right now just write anything you need right now okay let's move to the next question 157 right let's move to the 157 right what it says yeah first the first statement right see what it says copper sulfate dot 5H2 turns colorless on heating yes this is a hydrated salt right copper sulfate 5H2O hydrated salt these are referred to as hydrated salt right it's a salt with some H2O molecules trapped inside it right this is a hydrated salt hydrated salt right this one is light blue in color light blue in color light blue solid hydrated salt right so what they are saying turn colorless on heating yes if you heat the stuff let's say with a temperature above 100 Celsius if you heat the stuff with a temperature above 100 Celsius what will happen these H2O molecules will release H2O molecules will release and you will ultimately come up with copper sulfate solid no H2O things no H2O things those will release as H2O gas moisture so you will find out you will come up with copper sulfate solid anhydrous copper sulfate is referred to as anhydrous copper sulfate lamai anhydrous copper sulfate is anhydrous copper sulfate right it is whitish right white residue right in the presence of H2O the copper 2 plus ions right come up with that that kind of aqua complex right the hexa aqua complex the hexa aqua complex of copper 2 plus is the light blue colored stuff right but when it has a solid right without water it is whitish right if it absorbs water it is the hydrated salt it is light blue but without water anhydrous copper sulfate it is kind of a white residue right okay so what it says see the first statement it says turns colorless on heating the statement is false right this is a solid yet right it's a solid so solids are not referred to as colorless stuff A solid without a color means it is white. Solid without a color means it is white, not the colorless, right? It is white, right? Don't take it as colorless. So first statement is false, as they are mentioning this one as colorless. That is wrong. It is white. Solids without colors means it is white. Those are white, right? Okay. Right. Second statement. See what it says. During the process of dehydration, copper 2 plus reduces to form copper 1 plus. No. Dehydration means just removing water. Dehydration means just removing water. There's no such redox reaction occurring there. Right? Dehydration means removal of water molecules. Removal of water molecules. Right? No redox process there. Right? The color disappears because the anhydrous copper sulfate is formed, right? Not because of copper 1 plus is formed. Yes, we know that copper 1 plus stuff are normally colorless. The aqueous solutions are colorless. The copper 1 plus aqueous solutions are colorless. We know that, right? Copper 1 normally the solid stuff could be referred to as whitish. We have few colored things as well when it comes to solid stuff with the copper 1 plus even, but all the solutions of copper 1 plus are colorless. The D10 situation, right? So that is known, that is okay. But here the color disappears not because of formation of copper 1 plus, right? That is because of the thing converts to the anhydrous salt, right? Anhydrous salt, right? So that is the thing we should know here, right? So the second statement is false. No, second statement is false, right? So first statement false, second statement false. So answer number 5. Right now. So that is the 157. Let's go to that. Right. Quickly move to the 158. First, the first statement. Right. See what it says. Fe2 plus do not get precipitated in cation analysis. Yes, that is true, no? Fe2 plus won't get precipitated in cation analysis, right? In the group 3 analysis, we convert the Fe2 plus Fe3 plus and get precipitated as a hydroxide, but not as the Fe2 hydroxide. It will be precipitated as Fe3 hydroxide after oxidation by the conch nitric, right? That is what happens there, right? So we can take the first statement as true, right? Right. Fe2 plus precipitate. So let's say it's like this: precipitate with Fe2 plus cation. Let's say like that, right? Precipitate with Fe2 plus cation can't be found in group analysis. Right? In group 3, what it does is, in group 3 analysis, right, what they are doing is the Fe2 plus cations will convert to Fe3 plus with the addition of conch nitric and heating. Right? Then, right, it gets precipitated with the addition of NH4Cl in the presence of NH4OH, right? With the addition of this reagent as FeOH3 is kind of a low KSP hydroxide, it gets precipitated, right? That is what happens there, right? For the Fe, that is the fate of the Fe2 plus cations in the group analysis, right? Low KSP hydroxide. Right? So if Fe2 hydroxide is considered as a low high KSP hydroxide, that is that can't be get precipitated here, right? That is why we can first convert it into the Fe3 plus and precipitate as a hydroxide, right? Right, yes, clear. So that is what happens for the Fe2 plus ions at the group analysis, right? So the first statement can be taken as true, as they do not get precipitated at the group analysis, right? And the second statement, what it says, if Fe2 plus get precipitated as Fe sulfide in group analysis, group number 2, no, it is false, right? Second statement is false. If Fe sulfide is not considered as a low KSP sulfide, right? Only low KSP sulfides get precipitated in group analysis, group 2, in group 2 analysis, right? So if Fes is not a low KSP sulfide, right? It won't get precipitated, right? So that is the situation there, right? It is said as if Fe gets precipitated, Fe sulfide. No, it is false, right? So true and false. That means answer should be answer number 3, no? Answer number 3. That is the review for the 158. Right, no? Let's move to the 159. First, the first statement. See what it says. Mg reacts with an aqueous solution of ammonium chloride to form H2 gas. See what will happen there. So magnesium, what they are saying, magnesium reacts with an aqueous solution of NH4Cl. NH4Cl aqueous. See what kind of products are possible here. So ammonium salts can be referred to as a combination of ammonia plus the corresponding acid. So it's a combination of ammonia and the HCl here, the corresponding acid of the anion. So what are the products there? First the ammonia will release. Then right, these two guys will react. So magnesium with HCl, right? Acid and a metal. If a metal reacts with acids, what will happen? The salt and H2 will be the products, right? So you will produce the magnesium chloride and H2 as products. So here we clearly see some H2 gas liberated. So some 2 is needed here to produce 2 hydrogens here, to be 2, right? So this is the reaction. So again, let's go to the statement. Manganese reacts with an aqueous solution of ammonium chloride to form H2 gas. Yes, that is true. That is true. So when regarding the ammonium salt reactions, basically you can consider it as a combination of ammonia and the corresponding acid. Right now, let's move to the second statement. See, hydrolysis of ammonium chloride produces NH3 plus ions into the medium. Right. So when it comes to ammonium chloride, it is actually contains NH4 plus ions and Cl minus ions, right? The combination of these two are referred to as the ammonium chloride. So when these NH4 plus ions added to the water, they will hydrolyze. Hydrolyze means react with water. Reacts with water to produce what? Basically, what happens here? Here, one of the H from here travels to here. So we know water is referred to as an amphiprotic species. Amphiprotic species, so can accept H plus, right? Amphiprotic. H plus and acting as a base here, right? And this is acting as acid here. This is acting as acid here. Release H plus, that means acting as acid. So what are the products there? So by releasing H plus from here, you will ultimately come up with the NH3, and by accepting the H plus coming from the NH4 plus, this will convert to H3O plus. H3O plus. So hydrolysis of ammonium salts provide some H3O plus ions to the solution. That is why we are saying that ammonium salts are acidic. Some reasons: providing some H2 plus ions to the solution, releasing H plus ions to other species. Right? With all these observations, we can say ammonium salts are acidic. Remember, those are weakly acidic. This is a double arrow reaction. Right? Right? So we can say NHO plus salts are weakly acidic. Double arrow in weakly acidic. Right? Not completely react to produce the ions, not completely ionized. Right? But still provide some H2 plus ions, so H plus ions to the medium, right? So hydrolysis of that thing produce H2 plus into the medium. That is true. Hydrolysis means reacting with water. That is true. So yes, first statement. Explain the second one, right? The H2 plus ions are produced means H plus ions are produced. Both are the same, right? H plus ions in water is referred to as the H2 plus, right? H plus ions in water is referred to as the H2 plus, right? Because H plus is kind of a cation with a very huge charge density. H plus means just a proton appearing there, so very high charge density is there. So those guys get stabilized by forming the H2 plus by connecting with water molecules, right? So H plus in aqueous solutions means the H2 plus, or H2 plus means the H plus in the aqueous solutions, right? So both are the same. H plus and H2 plus are both the same, right? So the second statement explains the first one then, right? The acidic nature of ammonium salts is actually described from here. From the hydrolysis situation, the acidic nature of ammonium salts are described. So that is the reason for release the H2 gas. when reacting with a metal. The acidic nature of ammonium salts, right? So that is described here. So we can take the answer as answer number 2, as the second statement explain the first statement, as it is explaining the acidic nature of ammonium salts. Answer can be taken as answer number 1 for the 159. Let's move to the 160. Right? First statement. See what it says. Right. Copper 2 plus and nickel 2 plus cations could be identified using a solution of aqueous ammonia. See what will happen? You have the copper 2 plus and nickel 2 plus. Yes, we can, no? So if you are at aqueous ammonia, as ammonia is providing OH minus ions to the medium, as it's a weak base, is able to provide OH minus ions to the medium. So these two hydroxide precipitates will form, and those are with different colors. Those are with different colors, right? So the dropwise addition will form this stream, right? If you are adding some excess of ammonia, yes, it becomes a bit hard, right? So both are coming up with some blue colored stuff, right? But anyway, right, with the use of dropwise ammonia, definitely you can identify, right? This is a blue PPT, while this is a green PPT. Definitely can be identified, right? So statement is true. So they are saying can be identified, no? Could be identified using the solution of ammonia. Yes, it is true. Let's move to the second statement. See what this is. Copper hydroxide and nickel hydroxide are soluble in ammonia due to their amphoric behavior. No, that is false. They dissolve in ammonia due to their disintegrating behavior. Right? Again, the same comment I have to go with, right? So, ammonia, the aqueous ammonia, is used to identify D7 to B10 cations as they form soluble amine complexes. Right? So, that is how the things will be identified using the ammonia. To identify the amphoric situation, you have to use some strong bases. I have written the same review earlier as well, right? Strong bases are used. The ammonia is not a strong base, right? This is just a weak base. Ammonia is kind of a weak base. This is not a strong base, right? To identify amphoric cations, even the hydroxides, as they form soluble hydroxide complexes. Right? So the NH3 can't be used to identify the amphoteric behavior. To identify amphoteric behavior, you need strong bases, not a weak base like NH3. So NH3 is used to identify the decentrate nature of your compounds, right? Remember that. So true and false. That means answer should be answer number 3, right? No? Right. Let's quickly move towards the next question. Right, 161. So 161, no? 161. The first statement. See what it says. Barium oxalate is soluble in HNO3. Even the barium oxalate is slightly soluble in water as well, no? Right. So barium oxalate is kind of slightly soluble stuff, right? And definitely it will dissolve in complete dissolve in dill acids, because C2O4 minus is not an anion coming from a strong acid. C2O4 minus is not an anion coming from a strong acid. So basically it will dissolve in dill acids, right? The point is, if the anion of the precipitate is not a strong acid anion, not a strong acid anion. So if it is not the SO42 minus, if it is not the Cl minus, Br minus, OI minus, that is the idea there, right? And then those precipitates will dissolve in dill acids. Remember that barium C2O42 minus is slightly soluble, right? Even not a precipitate, right? Anyway, it will completely dissolve in dill acids, right? As C2O42 minus is not an anion from a strong acid, it will completely dissolve in dill H plus, right now. So that is the idea. So barium oxalate solid is soluble in dill HNO3. They are saying the solid, right? So that means they may have come up with, right, some very greater concentration of Ba2 plus and very greater concentration of C2O4 minus, right? So that we can think of a solid formation, right? Anyway, the solid will dissolve in dill acids, right? As the anion is not considered as an anion coming from a strong acid, right? So the statement is true. So second statement. See what it says. CO2 minus ions could be removed by H plus ions provided by HNO3. Yes, that is the reason, Lavin. That is the reason. That is the reason. Right? So, when adding del H plus to the C2O4 2 minus ions, what happens? That will form H2C2O4, which is a weak acid. So that the C2O4 2 minus ions, right, from solution will be removed. Even the C2O4 2 minus ions and the precipitate there, right? So C2O4 2 minus ions from the precipitate even removed, ultimately form the H2C2O4, which is a weak acid. So that is what happens. So C2O4 2 minus ions are removed by H plus to form H2C2O4, which is a weak acid. What is this acid? This is oxalic acid, right? It's oxalic acid, right? Right. So that is why these precipitates will dissolve. Those anions are removed by the H plus, forming these weak species. Right? The reason is fully explained. Right? So anions of the precipitate will dissolve ultimately. So if you need some idea, some simplified idea, see what happens. Some oxalate, right? The H plus is added. These anions will be removed. I write like this. These anions will be removed by the H plus added, ultimately to form the H2C2O4. Right? So that precipitate dissolves. Right now? So both the statements are true and second one explains the first one. So answer is answer number 1. Which is the review for the 161. So basically here you should have some 2 of each plus. Now these kind of stuff won't happen with when you are with kind of Cl minus Cl. The AgCl won't dissolve in dilyl nitric, right? AgCl won't dissolve in dilyl nitric. Why is that? Because the H plus ions can't grab these Cl minus ions to produce the HCl. Right? දැන් ළමයි මේක මෙහෙම වුණාට හරිද AgCl වගේ එක dilyl nitrate දැම්මක dissolve වෙන්නේ නැහැ නේ. ඇයි වෙන්නේ නැත්තේ? dilyl nitrate එකකින් provide H plus ට අර AgCl වලින් Cl minus එක ගලවගෙන ගිහලා HCl හදන්න බෑ. ඇයි HCl හැදෙන්නේ නැහැ ළමයි? HCl is a strong acid. HCl is a strong acid means that guy will completely ionize in aqueous solutions. Completely ionize means that HCl won't appear as the HCl. HCl ඉන්නේ නැහැ කවදාවත්. HCl අර HCl bond එකත් එක්ක කවදාවත් හිටින්නේ නැහැ. HCl සම්පූර්ණයෙන්ම H+ and Cl- වලට කැඩිලා තමයි solution එකේ ඉන්නේ. ඉතින් කවදාවත් එනම් මේ විදිහට release වෙන්නේ නැහැ. නේ HCl is not formed. Actually HCl is not formed. කවදාවත් වර මෙන්න මෙහෙම හැදෙන්නේ නැහැ. H+ and Cl- producing HCl කියන එක වෙන්නේ නැහැ කවදාවත්. මේ කවදාවත් වෙන්නේ නැහැ. මේ වගේ වෙන්නේ නැහැ. ඒ HCl strong acid කියලා කියන්නේ මොකද වෙන්නේ? මෙයා සම්පූර්ණයෙන්ම ionize වෙන එකයි වෙන්නේ. කවදාවත් මේ පැත්ත රියැක්ෂන් එක පොඩ්ඩක්වත් වෙන්නේ නැහැ. ඒක කවදාවත් මෙහෙම H+ වලට බෑ AgCl වල වගේ තියෙන Cl වල grab කරන් ගිහලා HCl හදන්න. HCl can't be formed. But the weak acids they can. weak acid form කරන්න පුළුවන් මේ weak acid ලියන්න මෙහෙම. H+ දැන් අර weak acid ලියුවොත් ඔය ලියන්න මෙහෙමනේ. H2C2O4 මෙහෙම weak acid double arrow ලියන්න. weak acid double arrow ලියනවා කියන එකේ තේරුම මොකද්ද? That means reverse reaction is possible. Reverse reaction is possible. H+ connects with the oxalate ions to come up with the oxalic acid. But with HCl that is not possible. HCl කවදාවත් හැදෙන්නේ නැහැ මේ විදිහට. හැබැයි weak acid එකක් නම් නැත්නම් water උනනත් හැදෙනවා. ඉතින් හැදෙනවා කියලා කියන්නේ මේ reaction එක වෙනවා. That means C2O4 minus ions will be removed from the system. So that is how the precipitate dissolves. Right නේද? තේරෙනවද වැඩේ ඇයි එහෙම වෙන්නේ කියලා? එතකොට strong acid නෑ කිය නම් dissolve වෙන්නේ නැහැ. sulfate dissolve වෙන්නේ නැහැ. ඒ weak acid නෑට ඉන්නේ අනිවාර්යෙන් වැඩි set වෙනවා. strong acid නෑනේ මින set වෙනවා. OH minus set වෙනවා. හරි OH minus H+ එක ගිහලා water හදනවා. water කියන එක completely ionization එකකින් නෙමෙයි. HCl ඉතින් වැඩේ කියන්නේ ඉතින් අර anions ටික trap කරගන්නවා H+ එකේ. එතකොට ඉතින් මා precipitate ටික anions ටික නැති වෙලා යනවා. precipitate dissolve. Right? That is the idea there. Right, that is the review of the 161. Let's move to the 162. Hi. Yeah, 162 volt. First statement. See what it says. Fe forms yellow complex with water. Yes, that is true. This is true. Fe's complex is yellow, the water complex. FeH2O6 3 plus, right? It's yellow brown. So we can take the first statement as true. The second statement, let's see. The geometry of aqua complex of Fe3 plus is octahedral. Yes, that is true. The Fe aqua complex, right? That looks like this. H2O6, no? If the coordination number is 6, definitely octahedral. No other geometry is possible with the coordination number 6. Right? When coordination number equals 6, geometry equals octahedral. So both the statements are true. The second one won't explain the first one. The color is due to D transitions, right? That is not explaining here. So here the color is due to D to D electron transition, right? So the in a ligand field, right, the D subshell is split to two, no, right, split to two sections, no, so that D2 transitions can be occurred, right. That is how the color is originated. So geometry is a difference though, right. So two different things, right. So answer is answer number 2. Second one not explained in the first one properly. Right? So that is a review for the 162. Right. Quickly move towards the 163. First is first statement. See what it says. There are some salts which are insoluble in cold water but readily soluble in hot water. Yes, that is true. In our syllabus, right, only such 3 salts are known. Only 3 salts are known like that in our A-level syllabus. In A-level syllabus, only 3 salts which precipitate when cold and dissolves when heated. Those are the lead halides. Those are lead halides. PbCl2, PbBr2, PbI2. So we have such salts, right? So the statement is true. It says there are some salts which are insoluble in cold water but readily soluble in hot water. Yes, these things will dissolve in hot water. Right? Dissolve in hot water. Right? Okay. The second statement. See what it says. Enthalpy of solution increases with temperature. So, sometimes it is true, but sometimes it is false. This is not always true. It is not always true. They are telling this statement as a general statement. We can't take it as a general statement now. Right? When it comes to ionic salts, most of the times this is true. Most of the time this is true. But when it comes to solubility of gases in water, that is the opposite. That is the opposite. Right? So we can't take this one as a general statement. So let's take it as a false statement there. So they are taking it as a general statement. Right? So the thing is, for ionic salts, normally solubility increases with increasing temperature. Right? Some examples are these. The temperature is increased, the thing will dissolve. Right? Solubility increases. Right? Okay. But when it comes to gases, for dissolved gases, solubility decreases with increase in temperature. Gases dissolving in water, dissolving in water only by forming second interactions with water molecules. Some weak interactions, some kind of weak interactions. So those interactions will break easily when you have to heat the system. So trapped gas molecules will release from the water layers. So solubility decreases for the dissolved gases. The temperature is increased. Right? So, but when it comes to ionic salts, dissolution is due to two things. Dissolution is due to two things. Dissolution of ionic salts is first due to the lattice dissociation energy, the breaking of bonds in the ionic lattice, and then the hydration should occur. Due to those two things, the dissolution of ionic salts happen. But when it comes to dissolved gases, that is only due to the second interactions with water molecules. Basically, when increasing the temperature, those second interactions, the weak interactions will break easily, and the trapped gas molecules will release from the water layers, water bodies, right? So dissolution of gases will decrease with the increase in temperature. So we can't say, right, the enthalpy of dissolution increases with temperature. No, sometimes it will decrease when it comes to gases, right? Okay, so true and false. So answer should be answer number 3. Answer number 3, right? Now, let's quickly move to the question number 164, right? 164. That's the first statement. See what it says. This 164, right? Copper 2 plus forms a soluble complex, that is amine complex, with NH3 in basic medium. However, it is not possible to form this complex in acidified medium. That is true, right? To form kind of an amine complex, you should come up with some excess amount of NH3 molecules. Only in the presence of excess amount of NH3 molecules, those NH3 molecules will go inside to the complex by releasing the trapped water, right? By releasing the water ligands, the copper 2 plus will grab the NH3 ligands if only the NH3 concentration is very high in the medium, right? But in acidic medium, what happens? In acidic medium, the NH3 molecules will convert to NH4 plus, because NH3 we know it's a base, so will react with H pluses, acids, and forms the NH4 plus. So the NH3 concentration will drop, so that amine complexes are not forming there. So to form the amine complexes, by releasing water ligands and gaining amine ligands, ammonia ligands, you should maintain some greater concentration of NH3. That won't happens when the acidified medium is provided, as NH3 guys are converted into NH4 plus, as NH3 is basic, will react with acids, right? So the first statement is true. Right? This is what happens now. So copper H2O6 complexes, is that a copper? Yeah. No? will react with the excess of ammonia. So the excess ammonia here needed to form the amine complex by releasing the water molecules. To do so, we should maintain some high amount of NH3. Then this is what happens is, right, H2O guys comes out and NH3 guys go inside. To do so, some high amount of NH3 should be there, right, to produce amine complexes high concentration of NH3 should be there in the solution, right? But in acidic mediums, as NH3 is basic, it reacts with the H plus in the medium to produce the NHO plus. Molecules consume to produce NHO plus. So NH3 concentration drops. So amine complexes won't form. So amine complexes hard to form or won't form. Or the amine ligands inside the sphere starts to come outside when the NH3 pressure drops, right? To form the NH3, to come NH3 inside the complex, to move these NH3 guys inside the complex, basically you should have some greater pressure around the complex. That is how the NH3 guys are able to go inside the complex by removing the H2Os. But if the NH3 pressure drops at the surrounding complex, what happens is water molecule starts to come inside, removing the NH3 to releasing the NH3 to outside. That's what happens when the NH3 concentration drops. That's what happens when the medium is acidified. Right? Okay. So the first statement is true. This is what happens. In the acidic medium, free molecules of NH3 are not available due to formation of NH2 plus ions with H plus. Yes, that is true. So that is the reason. That is the reason. So this is the explanation actually coming up in the statement 2. So second statement is also true. So that explains the reason for this first statement. So answer is answer number 2. Right? Right, let's move to the last question there. 165. First, the first statement. See what it says. SO2 cannot be used to identify copper plus 1 and the copper plus 2. So that is false, no? That is false. Last day also we had discussed about this thing. Right? What happens with the two situations? If you are coming up with copper 1 plus, that will react with the SO2. So copper 1 plus will oxidize to copper 1 plus and SO2, no? Copper 1 plus and SO2. So SO2 in aqueous solutions provide SO3 2 minus ions to solution, right? So SO2 gas in aqueous solutions. What happens? SO2 with water plus produce H2SO3. The H2SO3 will provide the SO3 2 minus ions to solution, right? So this can be used to precipitate the sulfides. Right? Okay. So that is what happens here. So with this, you are able to form the Cu2SO3, which is a white PPT. This is a precipitation reaction, right? This is a precipitation reaction. SO2 gas in aqueous solutions means SO3 2 minus ions. SO3 gas in aqueous solutions means SO3 2 minus ions, right? That is the idea there. So what happens with the copper 2 plus? So here, copper 2 sulfide is not a precipitate possible. What happens is, the SO2 as it can get oxidized to SO4 2 minus. While that happens, this copper 2 plus get reduced to copper 1 plus. Copper 2 plus will get reduced to copper 1 plus. And then the excess of SO3 2 minus there will get precipitated with this one. Like this. Right? It's a reduction precipitation. So you have the plus 2 here. It first reduced to plus 1 and connects with the excess of SO3 2 minus ions to get the precipitate, and by that happens, SO2 will oxidize to SO4 2 minus. So it is kind of a redoxan precipitation. Right? So this one is kind of a precipitate, which is white. So we can clearly see some color change in the solution. Some color change in the solution. So here we are starting with this one's color, light blue solution, and ultimately you are ending up with some white PPT and a colorless solution. Some white PPT and a colorless solution. So at the earlier case, right, copper 1 plus things are colorless. Copper 1 plus things are colorless. No color change in the solutions. Right? Here some color change occurs. Light blue to colorless. Right? So we can differentiate the two with the use of SO2. Right? So statement is true. The second statement. Yes, SO2 is a reducing agent. SO2 is a reducing agent. OSO2 can act as a reducing agent. So SO2 get oxidized. SO2 get oxidized to SO4 2 minus. So the species which get oxidized is referred to as the reducing agent. So SO2 can act as a reducing agent. The statement is true. Right? So false true means answer should be answer number 4. No? Answer number 4. Right now. So that is a review for the last question.